that if X D a metric space, we are given a metric space, then that metric will induce a topology tau topology on capital X induced by the metric D. Here if we take X comma Y in capital X and they are distinct points, that is X not equal to Y. X not equal to Y implies distance between X and Y is strictly greater than 0. Let us, that is, in this case let us call say R distance between x of xy, distance between xy say divided by 3, which is strictly greater than 0, then it is easy to see that then the ball, see we have like in R2 x y, this distance between x and y is R. Yeah. So, if we consider the ball center at x, radius, okay, this R we have taken as distance between xy by 3, not distance between xy, and distance between this, again the radius of this ball, let us call then the ball center at x, radius R, intersection ball center at y, radius R is empty. That is, these 2 points x and y can be separated by this open set. This ball is an open set containing x, this ball is an open set containing y, so that they are disjoint. So, this point can be separated by open sets. So, more mean this is just easy to see that if we take, for example, if we take let Z belongs to ball center at x, radius R, intersection ball center at y, radius R, that is proved by contradiction. So, if we assume that intersection is non-empty, then we can take a Z in the intersection, then distance between xy less than or equal to distance between xz plus distance between zy. Now, z belongs to the ball center at x, radius r, that will imply this is less than r. Again z belongs to the ball center at y and radius r, so that is again less than r, 2 times r, but 2 times r, 3 times r is distance between xy, hence this will be strictly less than distance between xy. That is, we get a contradiction if we assume that this intersection is non-empty. So, hence whenever in this metric space X, if we take xy in X and X not equal to Y, then there exists an open set containing X and another open set containing Y such that they are disjoint. In a topological space, if we have a topological space say X tau, a given topological space, then suppose for any pair xy belongs to X, X not equal to Y, that is they are distinct points. For xy in X, X not equal to Y, there exist, here we cannot talk about open ball. So, what we mean is there exist open sets say U comma V in X, that is U V belongs to tau in X, satisfying the condition that is for x y in X there exists open set U comma V in X such that 1 U is an open set containing X, V open set containing Y, and they are disjoint. U intersection V is empty, that is X Y any arbitrary pair in our topological space X with X not equal to Y, then we can find an open set U containing X and another open set V containing Y such that they are disjoint. In such a case, such a topological space, we call it a Hausdorff topological space, or in short Hausdorff space. So, then we say that such a topological space X tau is called a Hausdorff topological space. In short, we say just Hausdorff space. So, we have already seen that if our topology is induced by a metric, then that topological space is a Hausdorff space. So, every metric space is a Hausdorff topological space. So, but in general the converse, that is if a topological space is Hausdorff, then that need not imply we can find a metric D on X such that the topology induced by D coincide with the given topology tau. So, suppose X tau, even if it is Hausdorff topological space, we may not be able to find a metric on X satisfying this property. In other words, just we can give an example of a topological space which is Hausdorff, but some properties of the metric will not be satisfied. In fact, later we see that there are spaces like here a point, another point can be separated by open sets. So, if you have a point X and a closed set A in a topological space, in fact further we will assume that every singleton set is closed. A point x which is not in A, then this can be separated, then we can find an open set containing x and a open set containing the set A, such that this U intersection V is empty. So, then such a topological space we will call it a regular topological space. In that, then we can prove that if it is a metric space, then it is a regular space. So, one can give example of a topological space which is Hausdorff but not regular. So, now it is easy to see that. So, the familiar topological space will take it X infinite set tau suffix f, we call it cofinite topology on X or the finite complement topology on X, which is defined as this. We have seen a set A belongs to this collection if and only if the complement, this we write it A, that is same as X difference A is finite. As a set, the A complement is finite, or A complement is the whole space, then only we can get empty set in our collection, empty set complement X, which is not finite because X is an infinite set. Then this is a topology on X. With respect to this topology X tau f, a topological space, that is the cofinite topology, is such that every finite subset of X is closed, such that in particular for X in X, singleton X is closed in capital X, and hence finite union of singletons. Every finite union of closed sets is closed, hence every finite set is closed, but this topological space is not Hausdorff. So, first let us see that how the finite set is or singleton set X is closed for each X in capital X. So, take proof of this, take small x in capital X. We have fixed an X in capital X. Aim to prove the singleton set X is closed. Closed means closed in our topological space X tau. X tau, this we denote by F for finite. Co-complement, the complement is finite. So, take a singleton to prove this is closed, that is to prove say U, the complement of singleton X, that is capital X different singleton X is, we have to prove that set is open. So, this is open. So, what is our definitions says a set, here we have taken U belongs to tau f, mean take the complement. Now, the complement of U equal to complement of singleton X complement, that means again that is singleton X, a finite set, a finite set. Hence, by definition the U complement is finite, or in that case that U will be open here, or even if it is capital X, that means empty set is open. Here this will imply U is open in X. So, that means singleton X is closed, singleton X is closed. Now, if we take any finite set, I mean non-empty, if empty set means that is closed, if it is a non-empty finite set means we can find a natural number n such that x1, x2, xn belongs to X and A equal to this. This is a subset of X. Then this can be written as singleton X1 union singleton Xn. Each singleton X1 is closed, that means finite union of closed set is again a closed set. Hence, every finite subset is closed. In fact, such a topological space we will call it a T1 topological space. A T1 space means every singleton set is closed. So, now let us see that this topological space, but the topological space X with tau f is not a Hausdorff, is not a Hausdorff space, that means not a Hausdorff topological space. That means what we have to prove? Give a pair x y in capital X with x not equal to y, then you give any open set U containing x and any other open set V containing y, then that intersection will become non-empty. That means the pair of distinct points cannot be separated by open sets. Here in fact, this you just take take x y, x comma y belongs to capital X, x not equal to y. Now, take any open set U, say take len, take x y and U any open set in X tau f containing X, such that X belongs to U. Similarly, V any open set in our topological space X tau f such that y is belongs to V. They are all already non-empty. So, that means our topology is such that the complement should be finite. So, because the second case is complement is the whole space will not happen here, U any open set in X. So, that is here U belongs to tau f means that is if and only if U complement finite or U complement is the whole space X, but U complement is the whole space means U should be empty, but U is an open set containing X, X is in U. So, this case is ruled out. Hence, in this case U belongs to tau f imply U complement is finite. So, similarly V belongs to tau f will imply V complement is finite. Now, let us see what will happen to U intersection V. Our aim is to see that this set is empty. What will happen if we take the, suppose this is, I mean it is trivial, suppose U intersection V is empty, then take complement both sides, then U intersection V the whole complement equal to De Morgan law, U complement union V complement, but we have U complement is a finite set, V complement is a finite set, hence this union is also a finite set, only union of two finite set. This is a finite set. That will imply our space, the complement of this is the whole space, U intersection V empty complement the whole space. That means the whole space X is a finite set, but our assumption is X is an infinite set. So, in this case when X is infinite set, then the X tau f is not Hausdorff. Of course, it is trivial that what will happen if X is finite set, then the topology is what is called discrete. That means every finite set is closed, that means complement is also a finite set. So, complement is open, that means every set is both open and closed. So, that is discrete space. In particular, if we take x y, suppose in the discrete space, that is take X is any set or take X non-empty, tau discrete topology on X, that is tau equal to the collection of all subsets of X. Then we know that this is a topology on X known as discrete topology on X. Now, here it is obvious for x y in X, X not equal to Y implies we can take singleton X is an open set in this topological space, singleton Y open, X not equal to Y, that means intersection is empty. That is our U is, take U equal to singleton X, an open set containing X, V open set containing Y such that U intersection V is empty. Hence, every discrete topological space on X is Hausdorff, that is this is Hausdorff. We are assuming that X non-empty. So, if our cofinite topology will become, in this case if X is finite set, cofinite topology is nothing but discrete topology which is Hausdorff. So, we want non-Hausdorff, we have to take X as an infinite set. Now, just we will recall again quickly, see what is the properties of this T1 space. We have seen that Hausdorff imply T1, Hausdorff implies T1, meaning is if a topological space is Hausdorff, then every singleton set is closed in X, that we have seen. Other symbol result, a topological space X tau is a T1 space, is a T1 space if and only if the following conditions are satisfied, namely for x y in x, x not equal to y, they are distinct points. Then now we may not able to get open set U containing x, another open set containing y such that they are disjoint. Now we demand in a weaker sense. So then there exist open sets U comma V in capital X, that is T1 if and only for x y in x, x not equal to y, there exist open sets U comma V in x, that means U V belongs to tau such that 1 x belongs to U, that is it is an open set containing x, but y is not in y, but y not in U. Similarly, y belongs to capital V, V is an open set containing y, but x is not in V. So that means whenever x y are distinct points, then we can get an at least one open set U containing x, that y should not be inside. Similarly, another open set V containing y, so that x is not in the inside V. So x is not in V, but we do not insist that U and V are disjoint. So you can see that immediate, if a topological space is Hausdorff, in fact we get an open set U containing x, another open set V containing y such that they are disjoint. That means yes, once x y in x, x not equal to y, there are open set U V in x satisfying the condition, yes, x is in U, but y is not in U, and second condition, y belongs to V, but x is not in V. So it need not be disjoint. So hence this condition will be satisfied. Hence in this sense, if a topological space is Hausdorff, then this condition will be satisfied. So this is a simple exercise, we leave it as a exercise, that is a space is T1 if and only if it satisfies these two conditions. Now we will see some nice property of this T1 space, that is we are given with a topological space x tau and a subset say A of x. So given, so this will call it as a theorem, given x tau a topological space which is T1. So that is, it is a T1 topological space, T1 space, that is every singleton set is closed, equivalently every finite subset of x is closed. T1 space, A will assume that non-empty, A non-empty subset of x, then a point x in capital X, a point x in x is a limit point a limit point of x in x is a limit point of this set A. So, in such case we write that is x is a element of the derived set, this we know. This we know that x is a limit point of A means what? For each open set U containing x, whenever U is any open set containing x, then this should contain at least one point of A other than x, that means U intersection A difference x is, this set is non-empty. This is our definition of limit point. Here not only it is, if it is a limit point of that is x in A dash, a point x is a limit point of A if and only if for each open set U containing x, the U intersection A is an infinite set. Either we can say U intersection A is an infinite set, that one point does not matter, or even U intersection A difference x is an infinite set. For that, so either the space is T1 space, if it is T2 Hausdorff space, we also say that it is a T2 space. The space is Hausdorff, implied is T1. So, hence either it is Hausdorff or T1, then for each open set U containing x, this U intersection A difference x is an infinite set. I mean, one way is trivial, which is trivial is if this condition is satisfied. Suppose for each open set U containing x, U intersection A difference x an infinite set, hence it contains U intersection A difference x contains at least one point of A other than x. In fact, it contains infinitely many points. So, naturally it will contain a point of A different from x. So, we will not repeat that. So, we want to prove that, assume that the space is T1 and assume that x is a limit point of A. So, given, so note that limit point need not be in the set A, given x in x, say that x is a limit point of A, that means x belongs to A prime we call. Now, we want to prove that this condition for each open set U containing x, this set should be U intersection A difference x is an infinite set. We will suppose this condition is not satisfied. Suppose, that means suppose for at least one set, for an open set U containing, for an open set U containing x, U intersection A difference x is a finite set. I mean, already we know that U intersection A difference x cannot be empty because it is a limit point. That means it is a non-empty finite set. So, hence let us say it contains some x1, x2, xn for some natural number n. It is a non-empty finite set. So, now once this set is non-empty, so here the complement of that set. Now, let us say this set is, say, capital F equal to that finite set. x1, x2, xn is a finite set. Note that it is important to here take a difference x, so that none of the xi equal to x, then x is not in capital F, because each xi is in U, but not in a difference x, that means xi not equal to x. So, x not does not belongs to F, hence F hence our x belongs to complement of this set. So, that is say V, or we can just say F complement. Capital F is a, because our space is T1, our set F is a finite set, that imply capital F is a closed set, and hence the complement F complement is a open set. This is a open set containing x. Already U is another open set containing x. Hence, U intersection V, V is F complement, is again a open set. This is an open set containing x. But what is our x? X is a limit point of A, that is our assumption. Assume that x is a limit point of A, hence now our x is a limit point of A, imply x is a limit point of A, that is x in A prime. U intersection V is an open set containing x, implies this open set containing x, this will contain at least one point of A other than x. So, U intersection V intersection A difference x is non-empty, correct. So, this is non-empty, that means what? There will exist an element y in this set U intersection V and y not equal to x. But what is this set? But this will get a now contradiction to the fact that, but U intersection V, our U is V is F complement, but but this set U intersection V intersection A difference x, see okay. This we already have U intersection A difference x is our F. So, this is can be written as V intersection U intersection A difference x, correct. So, this set is our U intersection A difference x, we have denoted by F. So, which is equal to this intersection, this set is F, but what is our V? V is nothing but F complement. So, F complement, this is empty. That means what? This set, this is a contradiction. So, we cannot find if, hence for this open set V, if we take U intersection V is also open set containing x, and in this case this set U intersection V an open set containing x, that intersection with A difference x becomes empty, but if it is a limit point mean it should be non-empty. So, here non-empty, but our set is here, this set is empty. So, this contradiction we arrived by assuming that there is a open set, suppose for an open set U containing X, this intersection is finite. If this is finite, then only we can get that F complement. A closed set, F is closed set, complement is an open set. So, we can arrive at a contradiction. So, hence this cannot happen for any open set. That means, hence for each open set U containing X, U intersection A difference X is an infinite set. So, this is true even for a T1 space. In fact, Hausdorff, in fact this space like T1 space, it is not in some sense very interesting spaces, in the sense that though it has some nice property like this, when X is a limit point, then for each open set U intersection A is an infinite set, but later we will see that if a space is T1 space, we can even like in the cofinite topology case, you can see a sequence in X, and we know already what do you mean by a sequence converges to X in a metric space. So, and we know that if a sequence converges in a metric space to an element X, that point X is unique. That means a sequence will converge at most to one point in a metric space. The same thing we cannot expect if the space is a T1 space. So, for example, again do as an exercise, even take R set of real, consider the cofinite topology, see what happens to 1 by n. See 1 by n is a sequence in R. So, more generally if a sequence Xn converges to X mean take any open set U containing X, then we should find a stage n naught belongs to n such that Xn belongs to U. This Xn converges to X mean for each U containing X, that is it is a neighborhood of X, for each there exists a stage a natural number n naught such that Xn belongs to U. For all n after that stage onwards, n greater than or equal to n naught, then we say that Xn converges to X, but that need not be true if a topological space is just T1, but it not a Hausdorff space. So, but if the space is Hausdorff, then such a situation will not arise. That is, if a sequence is given mean Xn will converge to X if Xn converges to X, conditional, and Xn also converges to Y, then X not equal to Y cannot happen. Then we can, we can find a open set U containing X, V containing Y, they are disjoint, but except finitely many all the Xn's are in U. Here similarly here, that will give you a contradiction. And also we have a notion called generalized sequence or what is called net in a topological space. This is quickly I will recall what is a, we should have a partial ordered set, we call it J, will assume a non-empty set with a relation, we can use any notation like usual less than or equal to in R. If you use the relation less than or equal to is a relation on J. This relation is such that for x in J, x less than or equal to x, for every x, such a relation is called reflexive relation for all x. And second is conditional. If x less than or equal to y and y less than or equal to x, this can happen only in the trivial case, that is x should be equal to y. This should imply x equal to y, that is symmetry will not happen except in the case y equal to x. X less than or equal to y, x not equal to y mean y cannot be related to x. So, this we call it antisymmetric. And transitive is if again conditional, x less than or equal to y and y less than or equal to z imply x less than or equal to z. So, that is this we call it transitive. If a J with a relation satisfying these three conditions is called a partially ordered relation, then J together with that relation is called a partially ordered set. In short, we call partially ordered set, set. Further, like in natural numbers, you give, so now we are given a partially ordered set. This is given J a non-empty set, this is a partially ordered set. Further, suppose that for alpha beta belongs to J, alpha beta belongs to J, any arbitrary element in J, there exists say some alpha naught belongs to again J. So, like taking a natural number, you give n1, n2, we can take the maximum. Here we do not know what do you mean by maximum. So, there exists an alpha naught belongs to J, say that alpha naught is greater than or equal to both alpha and beta, meaning is alpha beta both are less than or equal to alpha naught. If a if a partially ordered set has this additional property, then that partially ordered set is called a directed set. So, then like a sequence mean we know that it is a function from the set of natural number to x, that means f of n equal to x n for each natural number this. Now, instead of J is a directed set, in particular the n set of natural number with usual less than or equal to is a directed set. Then a function f from J to x is called a J a directed set, then any function from J to x is called a net in x. That is, if you take alpha belongs to J, then the image is f alpha, that we call it x alpha. Then we say that either we say that f is a net in x or f alpha is a net in x, or say x alpha is a net in x. Then we can define x alpha converges to x in a topological space x means same thing. Take any open set U containing x. If it is a sequence, there exists a natural number n naught. Here, yes, for each U containing x, there exists a alpha naught belongs to our directed set J, such that exactly same relation, such that x alpha belongs to U for all alpha after that stage. That means, whenever alpha belongs to J and alpha is greater than or equal to alpha naught, then this condition should be satisfied, meaning is alpha naught less than or equal to alpha imply this. Then we say that the net converges to X. In fact, this is in a topological space we replace sequence by a net, like we can prove that X is in the closure of a set in a metric space if and only if X in A closure if and only if there exists a sequence Xn in A which converges to X. Like that, here in a topological space X is in A closure if and only if there exists a net, that means there exists a function f such that this f alpha equal to x alpha converges to X. In particular, many cases if you consider all the open set containing X, the reverse set inclusion, that will become a directed set. These things we have included in the notes due to time. Thank you very much.